The following is an energy equation, or actually an equation for work that is extremely useful and so very cool if you really understand what's going on. And I think just to help you understand, I have here a picture of Fred and Barney. Okay, back in the day, they in their car, and they are traveling on a road, and that road obviously has friction on it. Because they had no tar roads in those days, but even tar roads have some friction on it. And we're just going to look at how much work are these two actually doing. How much work are these two doing? Well, to work out work, we would say that work is done by the force multiplied by the direction and multiplied by cos of the angle between the direction and the force that's applied. Now in this case we can see that the resultant force that's happening, so the force that they apply is being reduced. Its effect is being reduced by friction. The force due to friction. And therefore the resultant force, that resultant force is what is going in the direction of their movement. So the force that's actually being applied, the applied force will always be made smaller by friction. Friction is in the opposite direction as the applied force. Okay, but the applied force is moving this thing forward. So in other words, the distance that they are traveling is in the same direction. In other words, the angle between the resultant force and the direction they're traveling is 0. Therefore, we just get this following formula. So I just multiply in my d, and I get the force of applied, and let me just write it smaller like that, multiplied by the distance minus the force. So this is the total work done. The total work done at this point is the force of the applied minus the force of friction multiplied by the distance. And this I see, okay, in other words, the total work done is the force of the work done by the applied force minus the work done by the frictional force, and that gives me my total work done. But what I do know about my total work done at this point, also another thing that I know about the total work is equal to the change in kinetic energy. The total work I do is equal to the change in kinetic energy. So far I've got this formula that the total work done can be replaced by the work of the applied force minus the work of friction is equal to the change in kinetic energy. And that means if I just want to see how much work is Fred and Barney doing, because they are applying a force, I need to take, and now I just add the work done to friction on both sides, and I see, well, the total work that these two do can be calculated by looking at how does their kinetic energy change, because some of the work that they do goes into accelerating their car, and some of the other work that they do gets lost due to friction. So obviously, and you can imagine yourself, if you were on a bicycle, okay, and you go over a road with a lot of friction, okay, your speed decreases, or your velocity decreases, because you have more energy or work that has to go into, and that's actually what happens here. the bigger this value becomes, the smaller my change in kinetic energy is. So even though I'm applying a lot of force, most of my force gets, and the word that they use is dissipated. Friction is a dissipative force, which means it steals the some of the forces that's in the positive direction. Now let's assume that Fred and Barney is going uphill. Okay, they're going uphill, so now they don't just have to overcome friction with their applied force, they also have to overcome gravity that is pulling them downhill. Okay, so to understand this a little bit better, let's just look at this triangle that just represents everything and understand what is what. Here we have H0, which represents their height that they start, and H1, which represents the height that they finish off at, which means that the difference between those two heights represent the change in height, or how much they've traveled vertically upwards. Okay, in other words, that this distance along here would be H1 minus H0, just subtracting those two heights. So if they were on 50 meters above the ground, or above the level, and now they're at 100 meters, 100 minus 50 leaves me with 50. Okay, now just drawing a little force diagram. Let's just look at what forces we have acting on here. So we've got the force that they apply in the direction of their movement. Then we've got the force due to friction, and we also have the force due to gravity. Now we know that that is calculated with mass times the gravity acceleration. Okay, now the problem is that this is our direction that we're moving in. We're moving in that direction, and to work out the work that we do, we need to consider the force in the direction of the travel, or the direction of motion. And that is why we are going to look at the components, two components of this force. One component is perpendicular. One component is perpendicular, and we know that the force perpendicular to motion doesn't do any work. And the other one is then, the other component is then parallel to the motion, and we just see it's in the opposite direction. So here I've drawn it, so let's call this force due to gravity that is parallel and force due to gravity that is perpendicular. And we can take these three vectors and put them in a triangle, and the triangle that we then left with looks like this. So you'll see here we assume that the angle is theta. The angle is theta. So if that angle is theta, then this angle would be theta, or in this picture that would then be this angle. Which angle is that now? This angle. That angle is theta, so this angle is theta. That angle is theta. We want to work out what is the force due to gravity that is parallel. We know that this value is m times g, and then the force due to gravity that is parallel is opposite that angle. So in other words, I find that the force due to gravity is parallel. I use my right triangle for sine is opposite over hypotenuse, which means if I want the opposite, which is what I'm looking for, I take my sine theta multiplied by the hypotenuse. So I say this is the mass times gravity times sine of that angle. So this is the value of the force in the direction. And I see as well, if I'm traveling uphill, that is against the motion, in the opposite direction of the motion, which means it's also subtracted. Now, putting all this together, let's go to our picture. What is the total work that Fred and Barney is doing? So the total work that Fred and Barney is doing means we must take all of the forces, the total forces, multiplied by the distance that they travel. We say they're traveling distance from here to there is the value d. Okay, but the total forces acting on is the force that they apply minus the force due to gravity, due to friction, minus the force due to gravity that's pulling them downhill. Okay, in other words, that's parallel to the surface, multiplied by distance. Now we can go and multiply that in, just like we did before. We just now have an extra force that is considered, and that is the force due to gravity. And I'm just going to replace that with m times g times d times sine of theta. Now on here we can see, okay, the force that's applied times distance means that that is the work that these two are applying, that Fred and Barney are applying. And then the force due to friction is the work that they have to do to overcome friction. Okay. And then this would actually be the force, the work they have to do to overcome gravity. But before we continue with that, let's just look at something very curious. If I look just at these two fractions, d times sine, so let's say d times sine, if we were to calculate that value, we get a value of, not 0, O. I get a value O. We'll see why I choose O in just a minute. Okay, so dividing both sides with the d, I see that sine of theta is equal to O divided by d. Now that means it's opposite over hypotenuse. Okay, if I go back here to the picture that I did, there's theta. So sine of theta is opposite over hypotenuse, which in this case is d. Okay, which means that O can actually be replaced. O represents the height, their change in height, from h0 to h1, which means O can actually be replaced in this case with, in the original case, d sine theta. O can actually be replaced by h1 minus h0, because A represents the opposite side of that triangle, and that opposite side of that triangle represents their change in their height, which means that this is what I'm going to do here. I'm going to replace sine of d sine theta with the change in their height, h0 minus h1. And if I continue just to multiply in these two, to simplify that, I get that the work of the applied force minus the work of friction minus, and then in here I get mass times gravity times height. I wonder if that looks familiar to you. Mass times gravity times height 0. This is the formula for potential energy. My potential energy after minus my potential energy in the beginning, because this is the potential energy they had when they started, that is the potential energy they have when they ended, which means that this can actually be the change in potential energy, which makes it that the total work that's being done is equal to the work of the applied force minus the work of the friction, okay, minus the change in potential energy. And we know that the total work done will be equal to the change in kinetic energy. And this means if I'm going to solve the applied force, I see that the work force that they apply, and now we just take the two other terms to the other side, I see that the total work that they do goes into changing their kinetic energy, in other words their velocity, minus changing their potential energy, in other words their height. So if they are going upwards, obviously they need to put some energy into overcoming gravity, plus the work that has to go into friction. So their work that they are applying gets distributed, some into changing their kinetic energy, some into changing their potential energy, and some in overcoming friction. And that is where this formula comes from. And if I'm going to do one or two examples, you see how powerfully useful this formula is. Let's look at some examples in the next video.